Welcome back. Now that you understand why we need batteries in off-grid system, it's time to learn a bit more about some important characteristics about batteries. The learning objective of this video is to understand some parameters that we use to characterize batteries, like the important performance and operation parameters for batteries. Rated voltage, rated capacity and rated current, energy capacity, rate of dischargings like C rates, state of charge and depth of discharge, cycle efficiency, voltaic and coulombic Faraday efficiency, cycle lifetime and its temperature dependence. These parameters are important to be considered when choosing a particular type of battery for a PV system. Let's start with the voltage rating of the battery. The voltage at which the battery is rated and is supposed to operate is called the nominal voltage. This is basically the open circuit voltage of the battery. The so-called solar batteries or lead acid batteries or lithium-ion batteries for PV applications are usually rated at 12 volts, 24 volts or 48 volts. However, it should be noted here that this voltage may actually differ from the battery's rated value based on its current state of charge and whether or not the battery is charging or discharging. The next parameter is the battery capacity expressed in amp hours or milliamp hours. When talking about battery capacity, the term refers to the amount of charge that the battery can deliver at the rated voltage. The capacity is directly proportional to the amount of electrode and electrolyte material in the battery. This explains why a small cell has a lower capacity than a large cell that is based on the same chemistry, even though the open circuit voltage across the cell will be the same for both. From this we can understand that the voltage of the cell is more chemistry based while the capacity is based more on the quantity of the active materials used. The third parameter that is used to characterize a battery is its rated current expressed in ampere or milliampere. This is basically the maximum current the battery can handle. Currents exceeding the rated current may damage the electrode of the battery. When talking about the battery capacity, we saw that it is measured in ampere hours or milliampere hours. Although that charge is measured in coulombs, ampere hours is just another unit of charge, since 1 coulomb is 1 ampere second and 3600 coulombs is 1 amp hour. For batteries, amp hour is the more convenient unit because in the field of electricity, the amount of energy is usually measured in watt hours. For example, a 10 amp hours 12 volt battery can deliver 1 amp for 10 hours at a voltage of 12 volts. Thus from the above set of parameters we can define the energy capacity of a battery, which is expressed in watt hours. The energy capacity of a battery is simply given by multiplying the rated battery voltage measured in volts by the battery capacity measured in amp hours. For example, a 100 amp hours 12 volt battery will have an energy capacity of 1200 watt hours. Next is the C rate of a battery. The C rate is a measure of the rate of discharge of the battery relative to its capacity. It's defined as the maximal capacity that can be drawn from the battery in 1 hour divided by the battery capacity. For example, a C rate of 1 for a 10 amp hours battery corresponds to a discharge current of 10 amps over 1 hour. And a C rate of 0.5 for the same battery would correspond to a discharge current of 5 amps over 2 hours. In general, it can be said that a C rate of N corresponds to the battery getting fully discharged in 1 over N hours, irrespective of the battery capacity. To design PV system, it's also very important to know the efficiency of the storage system. For batteries, usually the round-trip efficiency is used, which is given as the ratio of the total storage output to the total storage input. For example, if 10 kilowatt hours is pumped into the storage system during charging, but only 8 kilowatt hours can be retrieved during discharging, the round-trip efficiency of the storage system is 80%. The round-trip efficiency of a battery is basically a result of two battery losses. Thus this efficiency is broken down in two efficiencies. First is the photovoltaic efficiency. It is defined as the ratio of the average discharging voltage to the average charging voltage. I don't want to go in detail too much, but a battery can be modeled as a voltage source with a series resistance. This means that the actual voltage of the battery will be different to its open circuit voltage during its discharge or charging process. Thus, during the discharge process, the voltage of the battery will be less than its open circuit voltage. This is because of the voltage drop that occurs inside the battery when the current is being charged. But on the contrary, when the battery is being charged, the battery voltage will be slightly higher than its open circuit voltage. This is to compensate for the voltage drop that occurs inside the battery and to drive the reverse chemical reactions to charge the battery. The next type of efficiency is the Coulombic efficiency or the Faraday efficiency. It's defined as the ratio of the total charge extracted from the battery to the total charge put into the battery over a full charge cycle. There are always some losses that occur during the power dissipation of the electrodes and imperfect chemical energy conversion. Finally, by combining these two efficiencies, we can obtain the battery efficiency which we saw a while ago. It's defined as the product of the voltaic efficiency and the Coulombic efficiency. When comparing different storage devices, this round-trip efficiency is usually considered. Since this efficiency is a product of the voltage losses and the charge losses, it includes all the effects of the different chemical and electrical non-idealities occurring in the battery. I've said before that the voltage of a battery mainly depends on its state of charge. Now we will learn what this state of charge means for a battery. State of charge is defined as the percentage of the battery capacity available for discharge. Alternatively, we can also define the battery capacity in terms of how much it has been discharged. It's called the depth of discharge, or DOD. It is defined as the percentage of the battery capacity that has been discharged. It is basically the remaining percentage that is not included in the state of charge value. The state of charge and depth of discharge values are essentially an important battery parameter that is used often in PV system designing. As an example, consider a 10 amp hours rated battery which has been drained by 2 amp hours. For this battery, it's said that to have a state of charge of 80% and a depth of discharge of 20%. From this we can see that both terms are complementary to each other. Next I will talk about the cycle life of the battery. Rechargeable batteries that are used in PV systems usually undergo many charging and discharging cycles over their lifetime. A cycle lifetime of a battery is defined as the number of charging and discharging cycles after which the battery capacity drops below 80% of the nominal value. Usually the cycle lifetime is specified by the battery manufacturer as an absolute number. However, stating the battery lifetime as a single number is an oversimplification because the different battery parameters discussed so far are not only related to each other but also depend on the temperature. From this figure we can see that the cycle lifetime as a function of the depth of discharge for different temperatures. For colder operating temperatures we can see that a battery has a longer lifetime over its lifetime. Further, the cycle lifetime also strongly depends on the depth of discharge, where it's higher for smaller depth of discharge. This means that the battery will last longer if the average depth of discharge can be reduced during its lifetime. While the battery lifetime is increased at lower temperatures, there is a downside to this effect. When comparing the battery capacity with its operating temperature, we can see that at lower temperatures the corresponding capacity is actually lower than at higher temperatures. This is because the chemicals in the battery are more active at high temperatures, leading to a higher capacity of the battery. Sometimes at such high temperatures even possible to reach above the rated capacity of the battery. However, such high temperatures are severely detrimental to the battery health. This brings us to the end of this video. At this moment you learned a bit more about batteries and the parameters that are used to characterize them. The learning objective of this video was to understand some parameters that we use to characterize the batteries, like rated voltage, rated capacity and rated current, energy capacity, rate of discharging, the C rate, state of charge and depth of discharge, cycle efficiency, the voltaic and Coulombic Faraday efficiency, cycle lifetime and its temperature dependence. These parameters are important to be considered when choosing a particular type of battery for a PV system. Later in this course, you will learn how to properly size a battery when designing a PV system. For now, in the next video, we will learn more about another important component in the PV systems which uses batteries, the charge controller. So, see you in the next video.